Okay, welcome back to the final lecture. We're in the home stretch. What I have left to do is prove this lemma before I can prove a theorem and another theorem. So this lemma is the low frequency lemma, where we prove this bound right here. And last time, sketched out how to prove this proposition, which is going to be our main tool in proving this lemma. So let's do that. So proof of the lemma. What I want to show, for instance, is CAQ low, the maximal function on L2 to itself is at most Q T inverse, right? Remember, T is a parameter between 0 and 1. The way we're going to do this is we're going to do the same sort of analysis that we did in Stein's spherical maximal function. Remember that we have the following bound from there. If I look at this dilation, I take the inverse Fourier transform of it, and involve with the spherical measure on the unit sphere, then this is at most T inverse times 1 plus x over T, at a point x. And then say to the minus 2d. This is for all t positive. And we're going to take a small t here. This relied on the dimensionality of the sphere. Remember the fact that if I took any ball of radius r and I intersected it with the sphere, it was at most r to the d minus 1 up to some constants. Okay. And from this, we get to form a maximal function, where you form your maximal function by taking dilates of this, as we did in the previous set of exercises. And so you get a maximal function, which we'll call low here. And this, because of the bound, this bound, implies that on L1 to weak L1, we have this domination by the Hardy-Littlewood maximal function. So we got this was at most T inverse times the L1 norm of F. And this is on RD. Great. And the transference principle allows us to upgrade that now for each Q. And we just get to say that for each Q, we have the same bound for CAQ low. All right. But again, we've localized a bit more than in what the Magyar Stein Wainger thing, Magyar Stein Wainger transference principle does. And actually, our T here is going to be Q times T. Okay, which you see, which you see right here above. Whoa, this isn't. I don't know why this isn't moving. Okay. We saw this. Oh, there, that's better. Okay. We saw this because the Q's are right here in the dilation. Okay. Using that, we actually end up having our bounds are all with QT. So we get a QT inverse here over QT and QT inverse here. And this implies the same thing. This implies that is true for any of the CAQs by the Magyar Stein Wainger transference principle. Okay. Let's go back. Great, so that's the lemma in short, and then summing over Q is the remainder, but I'll leave that for everyone. That's a very easy thing to do. Were there any questions about the proof of the lemma? Okay, give me a moment in case there were, just to catch my breath. Let's see how to combine these two things now. We had two bounds. We had a low frequency bound and a high frequency bound. Right? In the high frequency bound, oops, this should say high frequency, we have these two terms coming into play. This is our L2 bound. Great. You can see, well, if Q is like exceedingly large compared to T, then the dominating effect is really coming from this one. And vice versa, if T were much larger compared to Q, then this is the, sorry, if T inverse was much larger than Q, or vice versa, then we see the two term, one of the two sandbands is going to be much larger than the other. And in order to avoid that, like so that we actually are using both parts of what it means to be high, we're going to take Q to be basically T inverse. And so that's basically choosing these, we want to choose these two summands to be the same. And we do that, that just boils down to this condition. Okay, that's all I'm trying to say. We're going to balance those two bounds coming from the high parts by just making those two summands equal and finding when they are equal. Okay. Inserting that into the high frequency bound, we see that we get this. Okay, so we've fixed T to be of this size, and that's going to go into the low frequency bound as well. No, that should be low right here. Oh, right, okay. So when you do the low frequency, you end up getting a bound of Q squared because it was Q times T inverse. Okay, now consider our maximal function, C star, and we're going to look at when it's bigger than twice alpha. Alpha is between 0 and 1 initially, now it's going to be between 0 and a half, and I'm looking at 2 alpha instead. That's just a linear scaling, it's fixed, it doesn't depend on the radius at all or anything, not a Maxwell function. That's a fine, very kosher move to do. We're cool. And what that allows us to do is now we're going to split our Maxwell function into two parts, a maximal function over the low part and a Maxwell function over the high part, and look at when both of those are bigger than alpha. In order for the maximal function C star to be bigger than 2 alpha, at least one of those has to be bigger than alpha. So if you were just to ignore for a moment the measuring the volumes, right, we see that we have the following set containment, right? The points where it's bigger than 2 alpha are when the low maximal function is bigger than alpha or the high maximal function is bigger than alpha. It's contained in those two sets. And so when you look at the volumes of those sets, you can turn that containment into a sum of two pieces, a sum of two volumes. And how do we use this? Well, the weak 1-1 bound was exactly this thing right here. That's what that bound meant. Oh, got to turn on the lights again. Okay, so that's exactly what that bound meant. There's some constant that I wasn't worrying about, and we get this, pick up this power of alpha. Now, what did the L2 bound mean? By the Chebyshev-Markov inequality, it actually implies this other bound. Remember that this said that the L2, so C star high on L2 to itself was at most this expression right here, which when we take Q and T related in this way is just saying it's just that much right there. Okay. But the Chebyshev-Markov inequality tells us that you have to square that and multiply it by alpha to the -2 times the L2 norm of F. So we get these two bounds. And the beauty of the restricted weak type argument is that whenever you have LP, so if I take F to be, F is equal to the characteristic function of my set F, like I've chosen here, then this implies that any LP norm of F to the pth power is just going to be the cardinality or the volume of that function, of that set, right? This is because it's the sum, or in our case, the sum of f of x to the p, right? That's what that equals to. And that is just the sum of 1 of f of x to the p. But that equals just 1 of f of x, because this is always equal to 0 or 1. And 0 or 1 to any power is just 0 or 1 again. Now you combine these two and you get this expression. And you optimize this expression again, or you optimize again in this expression. The first optimization was here. Now the second optimization is balancing these two summands. And that's where we're going to choose Q to depend on alpha. It doesn't depend on the set at all. It depends on the threshold alpha, this altitude right here. So optimizing those two summands, we choose this to be true. That means equal to up to some implicit constants we don't care too much about. And that, of course, just means alpha is of this size, or in other words, Q is of this size. And inserting that into the above, what we see is this bound right here becomes the desired bound right here. Now you might say, okay, but I claim the same bound for alpha, not 2 alpha. You can just replace alpha by alpha over 2. That only changes the implicit constant here by a factor of a power of 2. And that's still the exact right exponent for alpha that we wanted, times the cardinality of our function f. So that's a very nice optimization to get what we want. Are there any questions on that? Right, so all the hard work went into proving the right L1 and L2 bounds in a way that you could then fine-tune exactly the right choice in between to get the bound that you want for this altitude alpha appearing in our restricted weak type inequality. So let's do the same thing for the Magyar Stein Wainger discrete spherical Maxwell function. Right. Just to remind you of that theorem. What do we have? We pick an exponent p bigger than d over d minus 2. And we say that there's some constant k. Don't know what it is. It doesn't depend on alpha. It doesn't depend on the set f. Right? F is a finite subset of ZD. And alpha is a number between 0 and 1, not including 0. And we show that this bound is true. The number of points where, that maximum function, this should be m, where m, of course, is the spherical maximum function, the discrete one. Yes. Of course, applied to a function, it's that. Great. And so whenever a maximum function is bigger than altitude alpha, it satisfies this bound. The number of points satisfies that bound. Great. How do we do this? The proof of this divides into 3 pieces. let's just run through it, and then I'll tell you how I think about this. This is a proof that is different from what ENSU did now, and what Magyar Stein Wainger did. There's going to be one small part where that's being changed, or actually there's two small parts that are being changed. Okay, much like we did with C star a few moments ago, instead of 2 alpha, we're going to split things up into 3 alpha, because I'm going to split things up into 3 pieces, which I'm going to call the head, the heart, and the tail, respectively. Okay, the heart of the matter was the previous theorem, where we proved a restricted weak type bound for the supremum for C star, right? In particular, what do we show? We showed exactly this part right here. So there was some lesson here that told us that this sub-level, super level set, its volume was bounded by this. Okay. And all right, that's the heart. We've done that, we've handled that. Now the question is, how do we make use of that information? Well, for that, we also know something about the error terms. Okay, so the idea here would be to get some appropriate L1 and L2 bounds. From the approximation formula, I already have very appropriate L2 bounds, which are the error terms. For my analysis of the C star, there's also appropriate low and high bounds there that were used to prove this part in blue, or boxed in blue. But the question remains of what is the appropriate L1 bound? When ENSU did this, sort of did this all simultaneously, where he took each average and he did the approximation and the error term together, and pulled out like low and high pieces there and compare them to the Hardy-Little and Maxwell function to get an optimization over 5 pieces. But I've done an optimization over 2 pieces already by singling out a bound for this. And now the remaining, there are going to be 2 more pieces coming up. So the head is, the idea here is to take some big lambda, okay, and to consider the first averages up to lambda. And I'm going to essentially treat those trivially. I don't really know how to handle those well. The whole game would be to be able to get a bound that's uniform over arbitrarily large lambda, right? Because then monotone convergence just says I handle the maximal function for the whole thing. But we don't know how to do that at the onset. What we do know how to handle is instead a maximal function overall for C's at this point. But we need to leverage that to the averages, the maximal function for the averages. So this A star is M. So what I'm going to do is I'm going to just trivially handle the first few averages. This is the head of my sequence. The first few lambda, I'm going to just apply the union bound. So I'll replace the sup by a sum, and and look at each one of those in L1, right? So I know each average is a contraction by Young's inequality. That is, if I look at the average in L1, it's bounded by the function in L1. And there are lambda such averages, because I'm treating them trivially. So I end up getting this bound by the Markov inequality. Okay. And now for the heart, which I break up what's left. I have a sup over all lambda and equals a sup over lambda less than my threshold big lambda, or it's less than or equal to that, plus a sup over all the lambda bigger than it. Right? And I break up each of those averages now into my main term, the C lambda, and my error term, the E lambda. And I know how to handle those E lambdas on L2 very well. I break up this sup into a sum over J in N, and I look at the sup over lambda, oops, and 2 to the j minus 1 lambda up to 2 to the j lambda. Oops, E. That's an E, very important. And I use what we proved about this on L2 and sum up over all those j's. When I do that, I knew that each of these would be like 2 to the j lambda to the 1 minus d over 4 plus epsilon. That's what the L2 approximation was. And when you sum up over the j, basically that just kills this part right here. And what I end up getting is this factor right here. And the Chebyshev-Markov inequality means that I square that, multiply it by alpha to the minus 2 and times the L2 norm squared of my function to get this bound for the error term. And what am I going to do for the main term? Well, I don't know how to handle just big lambda. I proved something for all of lambda. So just enlarge it to be a bigger supremum and use what we already know about that. Okay. Now, when you've done that, you end up getting these three bounds. And what you need to do again is optimize. How do I optimize? I take my function to be some characteristic function, and so that all of these terms are just the cardinality of that finite set again, so that I can then just optimize these three things right here. Well, what does that mean? That means we want to take these three things to be basically equal to each other, up to some unidentified constants that don't depend on lambda or alpha at all. The first inequalities, I just move one power of alpha over. I end up getting that. I end up getting this for definition for lambda. Okay, now I want to check and make sure that these things are balanced appropriately. Not one isn't out of whack with the other two. And when you do that, you compare with the first and the second term, first and third terms now, you end up getting the same thing, which is good. Now you plug all of that in, and you find up to this epsilon loss, which is coming in right here from the error term, you end up getting a bound that looks just like this. Okay, why could I do that? Why could I just throw back in that epsilon at the end, even though I optimized for these three things? Well, not including the epsilon right here was just to make my life simple when I have to figure out these sorts of exponents relations right here, right? There's a 1 related to this thing right here. But because alpha is always between 0 and 1, or including 1, I get to make it bigger, right? This alpha to a minus epsilon, and epsilon's positive, is only a bigger factor. Okay, so it suffices to do this, and at the end to conclude what I've written down right here. Epsilon is just positive, and I had to prove the statement for all p bigger than d over d minus 2. D over d minus 2 plus epsilon, I can rewrite any p as d over d minus 2 plus epsilon for a positive epsilon. And that is exactly what I need right here. Okay, but you may worry about that 3. That's not what the bound was claimed for. Again, you just send alpha to alpha over 3, and you end up getting at a loss of a factor of 3 to the minus p, you have what you desired. But I wasn't caring about those implicit constants anyways, and it just depends on p. It does not depend on alpha or the size of my set. So it's good. And that is the conclusion of the proof. Were there any questions about how to do this? Right. In lieu of any questions at the moment, I'll just mention. So this trick right here, this union bound trick, where you replace the supremum by the supremum by a sum on L1, and sort of this combined with this the head, the heart, the tail idea is actually very useful in similar problems. If you were to try and do you could look back at the spherical Maxwell function, the continuous one, and you can give an alternate proof using this sort of idea. And so the way you would have to do things there is you would discretize the set of radii, but that's fine due to the continuity properties of averages or the spherical averages. And then, you would, so that's discretizing, and then you could rescale and compactify things. So you actually just look at, say, all the radii between 1 and n, just the integers 1 and n, and then do this sort of argument and get a bound that doesn't depend on n. But it becomes very efficient when you actually have a Latinary supremum here. So what I'll end with is just a little commentary on future directions, since I haven't heard any questions yet. Or current, I should say current directions. So one question that is left over from the analogous continuous theory is, what would happen if I considered a Latinary discrete spherical maximal function? Right. So this is what I think one of Stein Wainger's favorite problems. I know he definitely likes it quite a bit. And what does that mean? What is a Latinary maximal function? It's just, I'm going to take a supremum over a Latinary sequence of radii now. I was parameterizing things by lambda, right? I have these A of lambdas, and I just choose my lambdas to be a set from to be chosen from a Latinary set or Latinary sequence. And that just means that it grows rapidly. Like a Latinary sequence is one such that lambda j plus 1 is greater than rho lambda j, where rho is greater than 1. And so right here, you see powers of 3, powers of 2 are all perfectly good things to choose here. And you could ask, well, what about the maximal function on these things? Well, each of these is always less than or equal to, that was weird, less than or equal to the sup over all lambda. Right? And we know that's bounded on LP for P bigger than D over D minus 2. So each of these is bounded on LP for all P bigger than D over D minus 2. And the question is, can you do better? Can you get some P less than D over D minus 2? We saw in general that, well, for this Maxwell function, you cannot. But for this smaller one, can you get a better range? You could also ask what happens in 4 dimensions. So I was going to say, in relation to the above the head part of the argument, that when you have a Latinary condition like this, I at some point said that, I replaced the sup by all lambda less than or equal to lambda by just looking at the sum. Right? If this, and I use that I use the trivial bound, this is at most lambda times the sup. Oh, that looks bad. Let me say this in norms. And let's say, that in norms. And then that's at most lambda times the sup of the norms instead of the norm of the sup. And if this set actually is, you're looking at some subset here, and say it's Latinary, then there are only log of lambda such things. And you suddenly have a much better bound on your L1. And you can use that quite effectively in this optimization process. And this led me many years ago, about 2014 or 15, to a new proof of Calderon's theorem, which says that the Latinary spherical maximum function is bounded on all P bigger than 1. And it actually gives a nice little endpoint result there. You get like an L log L space instead, or restricted L log L bound. Yeah. And then if you want to make further progress, the natural thing to do is actually to start going into the approximation formula, right? So that Latinary condition gave an improvement on L1. I said the game in all of this is you have something on the special exponents in harmonic analysis are L1, L2, and L infinity. Told you how to do something better on L1. Let's do something better on L2. So you revisit the Magyar Stein Wainger approximation formula, and if you just reorder, so I had this term out here, but I could just move it in. And what happens when you do is this thing is a Kloosterman sum. And that has some added cancellation for lambda. Now, unfortunately, that cancellation gets destroyed when you take a supremum over lambda, at least if it's over the whole sequence of radii. And you may have to, you could maybe do some other things. There's some other tricks you can do. I've done in some work to try and leverage that cancellation, but it's rather quite subtle, and we certainly don't understand it at the moment. But what you need to do in tandem with that, or what you would like to do in tandem with that, is also get a better bound on the error term here, at least if you want to touch 4 dimensions. Because when you're in 4 dimensions, this right here is just 0. And so we have lambda to the epsilon, and what we've proved. But Magyar and Stein Wainger managed to take epsilon equal to 0. So that's just a 1, actually, in their work. But that still isn't anything you can sum up geometrically in 4 dimensions. So you have to squeeze out a little bit more to be able to sum up. Yeah. The conjecture, or my conjecture for 4 dimensions, is that the maximal function, m, the analogous one in 4 dimensions, right, which would be taking soup over soup in all n, I guess. A soup in all 4n plus 1. So look at all the lambda that are 1 mod 4 and form that as your maximal function. Then m is bounded on LP of Z4 to itself for P, all P greater than 2. And why did I have this 4n plus 1 thing? If you remember from a long time ago, in 4 dimensions, any sphere of radius 2 to the j, so that lambda would be 4 to the j, has exactly 24 points on it. And that meant that we didn't get the boundedness of the Maxwell function, because you needed more points. You needed some spread of information there in order to have a boundedness for a finite p in the LP. This restriction to things congruent to 1 mod 4, or actually you could also just say, 1 mod 2, really. That avoids that two-adic obstruction. And so then it does have the number of points on these spheres grows like you expect it to be. And when you consider that, you apply the delta function and you look at the asymptotics for how this Maxwell function would grow, you would be leading to conjecture that it's bounded on all LP for p greater than 2. So I will leave it there. That's for some food for thought, and just say thank you very much.